can start. So today it's a pleasure to have Bhimsen Shivamoggi, who's a mathematician and a physicist. And as recently I heard from 8 years ago, started working on stellar winds. So he's going to give us talk about stellar rotation effect on stellar wind. So please start.
Thank you very much, Rechi. I'm very happy to be up here to do this talk. And most important, first and foremost, thanks to Srinivas Kulkarni for hosting me here and then getting me familiarized with a whole bunch of great people here. So I'm looking forward to a very productive time in Caltech, and I'm happy to give this talk, which also have a lot of Caltech connections, starting with Gene Parker, who got a PhD from Caltech, and I had a very serendipitous encounter with him. Actually, I'm not a physicist. I'm a career fluid and plasma theorist, and I kind of occasionally tangle with areas like atomic physics, astrophysics, physics, because they are wonderful areas of application of fluid and plasma theories. The preamble is Parker's statement in Nature Astronomy 2020. Soon after the first set of measurements came from the Parker solar probe, which is, as many of you know, first ever NASA named probe for a living scientist, and the first set of measurements returned this interesting observation, which is summarized by Parker. Parker said, an unexpected result from the initial orbit measurements at 35 solar radii and beyond was the presence of a large and persistent component of plasma flow in the azimuthal direction in the same sense as solar rotation. And Parker immediately, with his usual powerful intuition, mentioned that this will have a lot of impact on our understanding of how stars lose angular momentum. I want to express my thanks to many expert colleagues in this, including mentor Gene Parker and some of my graduate students and postdocs. I want to discuss here the role of the azimuthal stellar wind flow that was indicated by the Parker solar probe and the associated centrifugal driving scenario with the stellar rotation mechanics. For this purpose, I'm going to make use of the MHD modification of Parker model, and that brings us to Weber Davis, and then Everett Davis again was a Caltech physics professor. Right? And then for the case of when a magnetic field is primarily radial, the Weber radius, the Weber Davis slow magnetosonic critical point actually becomes the Parker sonic critical point. I want to show that the stellar rotation actually will lead to considerably enhanced stellar wind acceleration even for moderate rotators like the Sun. They will rotate. And for strong rotators, actually, the stellar wind experiences an immensely enhanced acceleration in a narrow shell near the star. So the stellar rotation causes actually what now one can think of a Laval nozzle analogy for this whole mechanism. How come we make notes on that? So the end result of this is that the rotation, stellar rotation leads to faster stellar intervals and hence enable protostars and strong rotators to lose angular momentum fast before they burst to pieces. And then, if time permits, I want to make some remarks on this situation that Parker's steady solar wind solution currently has a good correlation to large scale behavior on average of the solar wind, in spite of the fact that there is a lot of local noise going on. And this tends to indicate a certain robustness of the Parker solution. And indeed, Parker actually was aware of that, and he pointed out that it could be a stable attractor of this dynamical system concerning the solar wind problem. I will try to make some remarks on that. A few papers of mine that written on this. I want to now start with the basics, assuming that some of you would like to know the basics. I just want to remind everybody stellar wind is an independently continuous outflow of a hot plasma from a star, and it carries a stellar magnetic field in the space surrounding the star. Contrary to what one would have thought, stellar winds carry off a very negligible amount of mass from the star, but they actually transfer a huge amount of angular momentum. And that is why they are crucial for a protostar, because otherwise, without help of the stellar winds taking away the angular momentum, the protostars will break up with huge centrifugal forces. And here the picture of a big star in Orion Nebula. And next, I'll show a picture of the first ever, what now? Picture of how existence evidence for the stellar wind. Then there was a lot of debate going on. Some of you may be aware of. Nobody thought there was a solar wind in our solar system, but then all the indication, all the evidence indicated that there's a flow of gas coming from the sun. And the comets were all they had their tails going away from the sun those wind flow indicators and the whole airports. So Parker said without the wind coming away from the sun, it's not going to happen. So he put out the paper and Chandrasekhar was the editor of the known, and Chandrasekhar sent it to the referees, and both referees totally rejected, but then demolished Parker's any knowledge, understanding of the problem, and they told him, if you got anything on this, you go sit in a library for 2 years, read the journals, and then you come back. Chandrasekhar brought these reports to Parker, and said, hey, apparently Chandrasekhar called Parker instead of Gene. Hey Parker, look, I got these two referee reports, and then they both don't support what you've done. So what do you think I should do? Well, he was Chandrasekhar, it was Parker, right? But this such analogs typically don't happen. So Parker said, well, if you ask me, there are no specific criticisms. It's a general objection going on, so I would say you go publish them. So Chandrasekhar said, okay, and he went and published them. Rest is history. All right. At that time, when Parker was talking about the solar wind, there was no Hubble telescope yet, and then so nobody could witness any such things out in the sky. But now we have Hubble telescope, and actually it's the image of Hubble telescope. So there is a big star in Orion Nebula, which is spilling out stellar winds, and they're running into the interstellar gas over there and producing a whole shock. That's a clear evidence that there is a stellar wind. And Parker, that's the evidence for this the stellar wind. But then one got to explain how the wind starts from the star at a subsonic speed, and how does it accelerate those subsonic speeds? What's going on over there? Well, if you just thinking about a nozzle kind of thing, but then nozzle requires a converging channel for the acceleration in the subsonic regime, and a diverging channel for the supersonic regime. But there is in the interstellar space, that space is only diverging. There is no conversion going on. So how do you accomplish acceleration in the subsonic regime? In the subsonic case, Parker said there is a way to do that, and an NGS model to explain this. Now, then comes another complication, which is the corona and then the stellar wind. They are fully ionized and then highly electrically conductive. So the magnetic field lines, which are anchored in the coronal base, they remain closer in the stellar wind. And then, so when they rotate with the star, they enforce a rotation of the stellar wind, as if it was a solid body. Everybody guesses this will happen up to so-called Alpine radius, where the speed of the flow is equal to the Alpine speed. So this means if the plasma sits locked to the star up until the Alpine radius, that means when the plasma is coming out, ultimately it will be coming out from a place of high momentum inertia. So it will carry a big angular momentum. And the first set of observations from Parker solar probe actually indicated that there is a strong coupling of the solar winds to the rotation, and that will lead to enhanced angular momentum transfer. The MHA version of a Parker model, like I mentioned, was actually started by Morissette, Herbert here in Caltech, and Belcher and Becker in MIT. Three, the magnetized solar winds. And I want to now point out, I will make some remarks on how the azimuthal wind flow and it brings together the centrifugal driving scenario in the stellar rotation braking mechanism, how it will enhance the momentum. The Parker mechanism is using the thermal driving to convert the thermal energy in the corona to kinetic energy of the solar wind. With the azimuthal wind flow, I'm going to sketch a different mechanism, which is the centrifugal based on centrifugal driving, and that's going to actually drive the stellar winds to much higher speeds. And then, so this centrifugal driving is applicable to the baby stars, which are spinning really hard, and then fast rotators, and Parker's thermal driving mechanism is good for mid-range stars like the sun. In the Weber-Davis eventually version of Parker model, one assumes that the star is going to have a monopole magnetic field lies in the equatorial plane. And in the case of the sun, how this happens is the solar wind pulls the sun's multipole magnetic field into open radial configuration, and within a few solar radii from the sun surface, this arrangement resembles a split monopole with opposite polarity above and below the sun equatorial plane and separated by heliospheric current sheet. This model, Parker assumes a steady state with a complete, for the sake of simplicity, complete spherical symmetry above the star. So magnetic field and the variables depend only on the distance r from the star. And to make things simple, by the way, I want to mention again that in this talk is a little bit old-fashioned theories out of talk and not too many pictures. Right. So here is how the theory develops. So we assume plasma is fully ionized, infinitely electrical conducting, and it follows a fluid model of which perfect gas modes, and the gas flow occurs under isothermal conditions. That means pressure is given by pressure is proportional to density, constant proportionality is zero. And this isothermal thing is not really a bad assumption, because temperature doesn't. In the solar wind case, anyway, the temperatures don't drop a lot. Here come the equations: conservation of mass, and then but for the surface symmetric case, that equation implies low.
So I'm confused. Is it isothermal or not in the previous slide? I don't understand.
Isothermal.
So Soho says it expands to great distance, okay?
Yeah.
While the solar wind temperature
Drops
drops.
to a factor of 10 from the corona to Earth's orbit. So it
But
doesn't drop.
that's not isothermal.
Well, especially if you are sitting near the sun, this is okay. If you go far away into the distances, long distances from
Okay,
the.
so when you say isothermal, up to what radius is the temperature?
Let us say like 20, 30 radius is I'm thinking from the sun. So yeah, so
there's a region it's isothermal and then starts dropping.
Yeah, so this isothermality is only a nice working assumption.
Okay.
It is kept there to keep mathematics simpler. Otherwise, if you go outside than isothermality, like use a polytropic thing, things just become so complicated, and exact developments are then impossible.
Yeah, curiosity relative to that scale.
Yeah.
Where's the Alfvén surface? Where's the Alfvén surface?
Is the Alfvén radius.
Alfvén radius is I think it's like a 10 solar radii.
10 solar radii.
Yeah, 10 solar radii. Right. Okay.
The sonic point?
Oh, good question. And that is about the 5 solar radii.
So as long as you are isothermal up to the sonic point and the Alfvén point, then it doesn't.
Yeah, because typically, but as you will all notice, as I sketch the story forward, you will all notice that I like to remain close to the star, right? And to make the story simple and reliable. I like to remain close to the star. Right? Otherwise, the Weber-Davis model gets treacherous. It's not easy to do with simple theories. Right? Okay. So we got a conservation of mass. Gives us that nice condition rho r square dr. Gauss law gives us r square dr equal to just simple things. Okay, Ohm's law is, as you all know, G plus U 1 over C V cross V dot equal to eta times J. Eta is the resistor. It's equal. It is fully ionized and infinite electrical conducting. So right centered. So resistivity is zero. That means the total electric field is zero. And in conjunction with the Faraday's law, because we're doing a steady model, so there is no 1 over C dV dt on the right hand side. So if you combine the two, then we get this delta zero, which is in the spherical geometry. All right, okay. And now if we take this story to the close to the coronal base, and magnetic field near the coronal base, is radial. There's no azimuthal comma. So what that means is you only have one term on the right hand side, and you combine them, you got a Vp minus lambda. Omega is the angular velocity of the star, times Br equal to Vr. So if you go in the specific frame, that means Vp minus omega sine r equal to 0. That means Vp is not 0, which means you got a spiral magnetic field lines, which you see that what they call Parker goes into the predictance of what they call Parker spirals. Okay, and now come to the azimuthal, the momentum balance for the plasma fluid. So we have the fluid acceleration on the left hand side, and then the Lorentz force on the right hand side. There's no pressure gradient now because we're doing azimuthal direction, so we don't get any variations, flow field variations in the azimuthal direction. And this equation immediately integrates and multiplicates is beautiful constant of motion, and it combines the first term describes the gas flow, second term describes the field. So the field and it illustrates the field and the flow contributions to total angular momentum. L. That's a constant. Yeah. Now we put all the equations, we put all the results together, and we end up with we can call expressions for azimuthal velocity, azimuthal field. All right, and what you see over here is 1 minus ma square is the so-called Lorentz number. So it's a ratio of flow velocity to Lorentz velocity. Lorentz velocity is given by that. All right, and then also you notice 1 minus ma square for both for azimuthal flow as well as the field component. And I say, hey, at when ma is equal to 1, then we got a problem. So we got to resolve that. And that means any L is not going to be like eigenvalue. Any L is not going to be acceptable. Only L that makes the numerator also vanish at the same point. So that determines what the L is right over there. So L is at the Alfvén radius. L is equal to omega times Alfvén squared. Right. So until one hits the Alfvén radius, and what that means is the whole plasma is in a solid body rotation, so it means the azimuthal velocity is given by that. Right. And one may interpret the Alfvén radius as the lever arm length of the magnetic braking torque, with the implication that a stronger magnetic field enhances this torque, and then this increases angular momentum velocity. This magnetic braking idea was proposed by the eminent astrophysicist Sharman, who was the advisor of my previous sabbatical host Uriel Frisch in Nice Observatory. Okay, now we come to the radial momentum balance. Radial acceleration, pressure gradient, gravity term, Lorentz force. And now this was the equation put forward by Weber and Davis, but then Belcher and McGregor revisited this and put that in this nice form. And this is not in its final but now interesting forum, which is the next slide. And VA, just like VAR is the radial alpha in speed, this is the azimuthal alpha in speed. So now the flow, but the left hand side, the flow acceleration, and that's equal to the Lorentz force term over here. You notice instead of in the Parker case, you have only one resonance. You have only one resonance. So if V sub R is equal to the sound speed, but here we have two over here. And so usual sound waves, many of you know, in NHD they go into two sound waves. They are magnetosonic sound waves. There are two types: slow magnetosonic, fast magnetosonic. And I'm going to mention to you what they are on the next page. You notice over here that there is this radial alpha in resonance factor sitting over here. And this, if you drop everything over here, in the Parker case, in the hydrodynamic case, it is R minus R star. That means if you arrange to have V equal to the sound speed at R equal to R star, that's Parker critical point, then you have a smooth flow relation. And that was Parker's engineer's idea. And then those two sound speeds are given by this. So if there is no magnetic field, there is no MHD, all these are at zero, these two guys merge into one single and they just take away. A is the sound speed. R star locates the sonic critical point in Parker's model, which is given by GM over 2A square. And so when you look at this, R star just locates the point where the gravitational energy of the stellar wind is comparable to the thermal energy. And there is something very interesting about this, right? And which is, if you replace the sound speed here by speed of light, that gives you the event horizon in general relativity. See what I mean? So there are some interesting similarities going on. Okay, like I mentioned, this is a crazy thing to deal with, right? So I said we can't work like this. We got in order to make some reliable further developments. I said we got to simplify.
Remind us what's the relation between C plus, C minus, and VAR?
This one. Talking this one, right?
Yes.
These are the expressions for the magnetosonic fast, magnetosonic slow.
And what's the relation to VAR?
VAR is
What's the ruling?
yeah. This is the azimuthal alpha speed, and you replace V by R and the radial.
Okay, but I'm asking which one is larger, C plus? Which one is larger, C plus?
Oh,
C minus,
yeah, fast.
and VAR.
And then for the next. This side. So there's a fast, that's why it's a fast guy, and then this one is the slow.
Yes, so C plus is bigger, C minus is
Yeah, smaller.
and VAR.
But
The radial fan speed, where is that compared to C plus and C minus?
oh, typically, good question. You know what I mean? Typically, it could be between C plus and C minus.
Okay.
You know, but there are different cases to consider actually.
Both VAR and VAI, they're both between C plus and C minus.
Well, actually, it doesn't have to be. You get a different configuration depending upon where VAR will be.
Depends on the orientation, right? You get the Spider-Man like that.
Yeah, you see
the mask of Spider-Man, which is a zero in the orange.
Yeah, you see the old military books, you know, they put over there pictures of what happens when VA is less than A, VA is greater than A, and all that, you know what I mean? So, interesting kinematic.
Just think of Spider-Man's mask.
Yeah, Spider-Man man. Yeah. I wouldn't think about that. All right. Okay. So I said, okay, so now want to simplify it and let's get close to the star. Near the star, the magnetic field is radial. So for that case, see how much they simplify. Right? C plus was into the and then we have simply C minus then B generated to the star. And then so what now when DV is not present, then I show you back here. Yeah, but this guy is not there, and then GP will be the rotation. Okay, so when mechanical is radial, then you have rotation of the star. And this co-rotation was what started this whole story in the beginning. Okay, so for this situation, then what happens is the complicated equation that you saw over here a while ago. If this further equation it degenerates to the simple form given here. So if you know what happens if you know just drop this simple velocity, you're back to the Cartesian model. So what this means is um, in the neighborhood of the star, when the magnetic field is primarily radial, the Weber-Davis LHD model, it degenerates to the Parker model with just a centrifugal form added over there. So this is like the MHD effects have been renormalized in terms of co-rotation, right? So we start the MHD model, right? And then we realize that it is sufficient to deal with MHD in terms of its consequences, namely the co-rotation. So MHD introduces co-rotation, then we say goodbye, right? So this is very much like what happens in dielectrics in plasmas. So what happens over there is you got a bunch of charged particles, and then you introduce a test charge over there, and what it does it attracts particles of opposite charge and acquires a dressing, a shield. All right, and then when other charged particles come and shield this given test charge, and then outside the shield, the test particle is electrically invisible. Right, so instead of a bunch of, if you can think of the same thing for all other particles in the system. So what you have over there, you have either consider a bunch of charged particles sitting over there, or we replace them by a renormalized system of collection of shielded particles, and they have no electrical interactions. Right, so it's like you put the shielding and you switch off the electricity, and then same thing happens in the relativity too. You put in curvature to the space and continuum, then you can get the balance. Right. Okay. Introduce the rotation. Then you have this cubic thing over here. So what I propose then is let us we want to do some mathematics on that. So we got to introduce some appropriate non-dimensionalized quantities. So introduce a non-dimensional radius, and then argue that here that locates the critical point in the strong rotation case. R star is the distance that locates the critical point in the thermal driving case, and gamma is the ratio between the two. And alpha beta are some quantities given in terms of gamma. You will notice where they come. So right in terms of them, the modified Parker equation, it takes this form, right? And then this is the associated resonance over here. And instead of a linear term over here, you have cubic. And it so happens this cubic thing over here, it has one real root, remember that, and two complex conjugate. So this can be rewritten in this fashion. So the new resonance over here is when R equal to that also minus beta over there, PR will be equal to 8. So if you introduce this boundary condition, then you ensure a smooth flow development. Now for strong rotators, the critical point, that's the critical point right there. Alright, and alpha beta were let me remind you, they're right there. Right? And gamma is the ratio of the two critical points. So for strong rotators, Gamma has the angular velocity of the star in the denominator, so it's very, very small. And for that case, the critical point is basically near this is the strong rotator case. So this R tilde depends only on mass of the star, angular velocity of the star. There's no thermal effect over there. R star depends on the sound speed. The strong rotators, for the strong rotators, critical point is dictated only by the mass of the star and then angular velocity. Nothing to do with the stellar wind conditions. Yeah, for the strong rotators, basically what now are the critical point is given by that length R tilde. And then I just want to point out that actually the Weber Davis model, it got with a lot of physical simplification going on over there. And for ordinary stars, it doesn't look very reliable. But then for strong rotators, what happens is the rotation introduces flattening, right? So instead of a spherical thing, they become kind of a blade. And so the strong rotators in the solar system are there. Sorry, I put it in miles per hour. This is like I think 150 miles per second. Regular this one is like 200 something miles per second. And this is like 170 miles per second.
Mile per second is still not okay. Mile per second is still unacceptable.
But astronomers want miles per second. Right? And then these were the wild guys in our galaxy. But then recently I heard they found in this place there is this place called Large Meteorite Cloud. I got to mention to you that out in New South Wales, Australia, on a hilltop ranch, my buddy Tim Wells, I see large meteorite cloud and small meteorite cloud. They are so clear. The sky is so clear to see that. And apparently, large meteorite cloud in the Wild West, everything over there is crazy. From the star over there, apparently is going 1 million miles per hour. So, right, 1 million miles per hour. And then even the nursery over there in large meteorite cloud, I heard is wide. So they were saying that if we take that nursery in a large meteorite cloud and put it in the same place as the horizon, then it will shine so bright, so brilliant, it will cast shadow on Earth during the day. So brilliant. So meteorite cloud, I got all crazy things going on. Like I said, yeah, meteorite is the worst case. Equatorial diameter is 56% greater than polar diameter. So actually, there are better models for Weber Davis system. And then, like I mentioned, for the strong rotators, one critical point is determined just by the basic stellar parameters. Mass, there is no reference to sound speed. For the slow rotators, gamma now is much greater than 1. And in that case, the critical point is basically 500. However, if we connect it with the sun, which is a very moderate rotator like the sun, and the critical point comes out to be like when you include the sun's rotation, it is not R star like in Parker model, but it is 187. That means the critical point has gone deeper inside the corona.
Do you have a feeling for how strongly this would change if you actually had a very fast rotator? Because it would no longer be circular symmetrical. Have an alpha surface.
Yeah, but then I think it actually for the to do really reliable thing, you got to abandon center symmetry. Then I'm sticking to part following Parker. I'm sticking to part center symmetry for the sake of mathematical simplicity, so that we got a qualitative picture, and then we can go change things quantitatively.
So sorry for the fast rotating stars that introduce a couple of them. So the rotation speed is still slower than the sound speed.
Well, because for the strong rotators, the speed of the star it dominates the dynamics of the solar wind, stellar wind. Because Because like I mentioned,
So the pressure support in the surface is 5% pressure gradient in the star.
let me mention again.
No, okay, simpler way to look at it is, even in a corona of a million Kelvin, sound speed is only 100 kilometers per second. So once you exceed that, then, that becomes the dominant term. And since stars are basically, they can rotate as much as they want, but the surface temperature has nothing to do with, it's capped. The hottest star is maybe 50,000.
Yeah.
So the range of thermal velocities in a star are actually quite modest.
Yeah.
Whereas the range of rotation speeds is very divergent.
And the critical point for the strong rotators is determined only by the balance between centrifugal and direct energy. The thermal energy cannot compete with the centrifugal.
So let me ask a similar question to Elias. What you showed is that the sonic point goes a little bit inward, 10%, because of the rotation.
Because of rotation,
And
the critical
it's
point
only
comes in
10% because the rotation is not so fast.
Because for the sun it is very mild, but the thing is, even that is enough to bring it down.
Fine. But then, coming back to Elias' question, if I want to see in a realistic 2D or 3D case, this 0.87 will depend on angle.
Oh yeah,
And my
absolutely,
question is,
absolutely.
My question is
Yeah.
the deviation of 0.07 from 1 is 10%? Does it change considerably with angle? Or
Actually, it will, because as you probably know, the fast streams are coming out of the polar areas, and then the slow guys are coming from the equatorial areas. See what I mean? So there is a lot of latitudinal non-uniformity over there in the real star. You see what I mean? And then you also have this 2 weeks ago we had a full solar eclipse, right? And at that time you could see the regions, coronal holes. So that's where all these fast streams are coming out. The coronal belts is a place where the flow channels are not they are not diverging in a linear fashion like in a spherical geometry. They are diverging superradially. So a lot of fast stream action going on. The real star is a complete what now complicated detail.
yeah, but I'm not going all the way to the ridge.
Yeah,
I'm
yeah.
just trying to take your model problem.
Yeah. So the spherical symmetry is just to make things manageable mathematically. So you have a nice solution. That's the whole idea.
But then the outcome of your calculation is the deviation of the sonic point from the original part. And you got the answer is 13% change.
Yeah.
And I'm asking, is this 13% changing considerably with data or not?
Oh, it will. But this is crude. It's only what now?
But that would be hard to see because, you have to get out of the elliptic plane to actually make that measurement, whereas the particle probe is very much in the elliptic plane.
Yeah.
So
How to see is your problem.
No, I'm just saying. The observations are all in the.
That's what I'm saying. Observation is your problem.
Yeah.
I'm trying to answer.
Your question is what does that lead to the total sun slowdown? That's the one.
Right. So even for the sun, right, the effect of the consequences of rotation are considerable, as you see here in a second. Right. Okay. Okay.
Well, I take it back. There was a probe, Ulysses. Ulysses was a polar orbit specifically.
Ulysses is a polar orbit. That's right.
Yeah. So that would measure the polar component of the probe.
And there is a SOHO.
No, so is at L1.
Yeah. There are a bunch of. Okay. So what this story shows is that even for the sun, the critical point is below what the model indicates. Right now, so here comes the other consequence of that. So when the critical point comes below towards coronal base, then the region of supersonic acceleration becomes bigger. So with all the coronal heating going on over there, so it is like you are enhancing the afterburner action in supersonic regime. So anything that brings the critical points lower into the corona, it will lead to faster solar winds or solar winds, right?
Why is that? Because I thought you said this plasma is highly conducting.
Yeah.
So, yeah, so whether I go 10 from the sonic point, the traditional sonic point or 10% below, I'm still at the same temperature.
Well, the thing is that there is a greater region of where coronal heating can happen in the supersonic case. Because apparently the afterburner action, which is done in the supersonic portion of the rocket nozzle typically, it produces faster gases coming out. So it's like introducing extra heating in the supersonic region. So gases will.
No, but that's why I said that will only be true if the gas is not conducting well.
Yeah.
But if you tell me I have a gas which is conducting very well, then it's not the jet analogy is incorrect because that gas is not conducting. I'm assuming I took your statement that the conductivity is infinite.
Yeah, the thing is Srinivas, but then once we renormalized the effect of the magnetic field, MHD, and then we are pretending we're in a hydro, or pretending we're in the just neutral gases. You see what I mean? Because going back to the plasma again can make it more complicated because there are so many complications going on with plasma. The moment you say plasma, you got to deal with all electromagnetic effects. So keep the dynamics simple. That's why that was the idea. Okay. All right. Now this equation over here. Can be an exact solution. Yeah. Yes, there it is. Exact solution for the Parker model, in which we include the rotation of the star according to the co-rotation. Right? That's the exact solution right there. Right.
This is still in the spherical approximation or not?
What?
This is still in the spherical approximation.
Yeah. Spherical symmetry is the basic. We can't change that because I mean nobody has found a way to do analytics without the spherical symmetry until now. Okay.
I did some hydrodynamics non-spherical symmetry. I have some papers which are non-spherical.
Yeah.
Hydrodynamics.
Yeah.
Discuss.
No problem. Discuss chat with you. Right. But this is the scoop. Taking the Parker story one step further to include stellar rotation. Right. And I'm going to show a picture of that solution. So because it is exact solution, there is no need to the solution of that ODE. Right. So we can just plot that solution, and there it is. Right. And this red line here is the Parker curve. And you put rotation in the Parker model. I mean, for the sun, it already gets augmented. All right. And I go to fast rotator. This is how it goes. The flow acceleration happens in a very narrow shell, thin shell, near the star. It shows effect of strong rotation. And these curves here going to the left, rising to the right or the left or right, they're the efficient disks, which are gone weak.
So what are what are the other curves?
The accretion disk, the gases.
Accretion disk. Okay.
Yeah, the gases come from far.
Got it. Yeah, it's a reverse.
So the velocity rises near the star.
Well, but I'm confused. In one case the star is rotating. In the case of accretion disk, what does it mean if I choose your fast rotator?
So it's not an accretion disk, it's an accretion. Not a disk.
Well, sorry.
It's bonding.
Yeah, it's bonding accretion. Yeah. So it's a gas coming from farther out and then falling onto the star.
And that whole gas cloud is rotating.
The whole gas cloud is rotating.
Okay, well, that's a bit unrealistic.
Yeah. Now we go to the it's not
It's rotating at infinity.
What's that?
It's rotating at infinity, I guess.
Yeah.
Right, is it?
Yeah. But Okay, I would imagine, I'm not expert on equation, this,
So,
but I
but
would
the
imagine.
solution is really things like the angular momentum and large distances.
Yeah. The solution is that the gas is rotating with the star.
Even at large distances.
Right. That's very honest. Yeah, I mean, definitely up to the alpha radius
In the accretion case.
in the accretion.
Well, that's why I said it's unrealistic.
Yeah.
It's just a mathematical.
Yeah. Because, I mean, accretion, it so happens that I'm not looking for accretion solutions, but they just part of the wind solution. Okay, when you've got a very strong rotators, and the cubic thing or the cubic stuff on the right hand side becomes just case. So you have only these two terms over there, and you quickly see over here the resonance is that R equal to R tilde. That's the critical radius for the strong rotators. And then that's the exact solution for that. And I already shown a picture for that. Yeah, for the going back to the picture, we notice you put in rotation, the critical point moves to the left, lower in the corona. And then for the strong rotators, it is so way down in the corona. So if one can imagine that will really incite huge afterburner action. Okay, now comes to this is a theoretical speculation. Okay, anything that starts from subsonic speeds and accelerates supersonic speeds in ordinary gas dynamics means can't happen without a nozzle. Okay, so the question is where is this nozzle in the space outside the star? Because the space outside the star is only diverging, there is no convergence going on. So where is it? And Parker was speculating, but then this aerodynamicist is like closer somewhere over here in the LA area at that time, I think. He supported that, yeah, it's possible to visualize the level that nozzle mechanism in the space outside of the star. So superficially, one can actually see one nozzle type situation over there, but just because a nozzle type thing is happening over there doesn't mean it's a real nozzle, because we all know all that glitters is not gold. You'll see in a moment. There's an interesting contrast between the conventional Laval nozzle and the nozzle that is operating in the Parker model. Well, okay, this is the Laval nozzle, right? Convergence in the subsonic regime, divergence in the supersonic regime, right? And so if the flow hits sonic speed at the throat, then it will continue to accelerate to supersonic speeds. But if it doesn't make it over there, then it becomes a breeze. Okay. All right. I tried to. Well, these were Parker and Clausen had they had intuitive ideas about this, and I tried to quantify them. Okay. So if we really think there is going to be a effect on a Laval nozzle, how will its cross section look like? It will look like this. Right. That's the Parker model with the centrifugal acceleration. How we can figure that. So that gives you the cross section area of the nozzle. And then now we can integrate this and then given by this. Right? Okay, now if there is no solar wind damage going on, then this whole exponential term over here is just 1, and then what you have really is 4 pi square. Right? But then what happens is if we go back to the Parker equation and then throw away the flow acceleration terms on the left hand side, keep only the right hand side, which is the balance between pressure gradient and then gravity, and maybe then also centrifugal. Right? If we put that equal to 0, then you come up with the density profile, the famous Chapman density profile. That's right there. So Parker model is supposed to have put all the Chapman ideas away out of the picture, right? And then we are completely in the wind picture. However, Chapman density profile shows up in a Parker model, right? So that's why I say old soldiers don't die, they just fade away, right? So Chapman profile shows up over here, right? And the interesting thing about this is Chapman profile. I'll show you the actual numerical calculation of that one. Yeah, look at that. Actual numerical calculation of the fluid of the Parker density profile. It actually, what now? The dotted line is the Chapman profile. Completely, basically assuming that it is hydrostatic equilibrium, no flow. So and density profile for that is a dotted line right there. And Parker density profile with the wind flow is just working over there. You see that until you hit in the subcritical regime, until you hit the Parker sonic point, the two are indistinguishable. So the Parker density profile is very much like a Chapman density profile. And the nice thing about this is, please recognize, density falls steeply only until the critical point, and after that it's basically constant. All right, in the solar wind case, density drops only in the subsonic regime, in subcritical regime. After that, it is constant. So we come back here. We come back here. So in the subsonic regime, this drops faster than 1 over r square. So that will pull this down. So that means in the subcritical regime, this will decrease with r effectively. Alright? So you have a converging channel. Now what happens in supersonic regime? Like we saw in supersonic regime, Earth sub C is effectively constant. And that means the area now will increase like r square. So in supersonic regime or supercritical regime, you have a diverging channel. So it's like Mother Nature devised a real good rocket nozzle over there. And actually, if you want to go crank out more mathematical details on this, we recognize actually when we calculate the derivative of effective nozzle cross section, and you can show that in the subcritical regime, derivative is negative. In the supercritical regime, derivative is positive, like you anticipate for a regular Laval nozzle. So I tend to think I'm not going to go into details. I tend to think I'm going to summarize quickly and make closing remarks. Parker's development of developing a continuous acceleration from subsonic speeds in a diverging interplanetary space was ingenious. It all hinged on the fact that gravity is a retarding body force, and it is progressively weak from the start, and that was enough to when the near the star gravity is very strong, so everything falls right back to the star. All the density becomes really large near the star. So away you go from the star, density drops precipitously. So when that happens, the flow has to accelerate near the star to maintain mass balance. And then after the sonic point, density doesn't drop anymore. It remains constant, and area is diverging. In the supersonic case, the area diverges is accelerates. So this whole mechanism was set up in a very ingenious way. Too bad the referees didn't see that for Parker's paper. All right. My intention is important as soon as you go from the start. So there it is. So in this talk I worked on Davis model with the aim of clarifying the role of azimuthal inflow in the star rotation mechanics. And we saw that the way the solar rotation works in accelerating the winds is by kicking the critical points down into the corona, so the winds can experience stronger afterburner action. So basically, you are converting not only the thermal energy like the Parker model, but the centrifugal energy, rotational energy into the streaming energy. And like I said, Laval nozzle is a nice theoretical concept to think of, but it doesn't quite do it like the solar wind, because in the standard Laval nozzle, the flow is yeah. Um, Yeah, the conventional Laval nozzle, the flow is the flow acceleration is induced by geometry, the converging geometry, and then but then in the solar wind case, the flow acceleration is due to the compressibility. So it's exact opposite of the rocket nozzle. So in the rocket nozzle, in Laval nozzle, the flow is geometrically controlled in the supersonic case, and compressibility controlled in the supersonic case. The other way around for the solar wind. I want to talk with another kinetic connection. Right? For several years earlier in my career, I used to do a lot of perturbative calculations. Right. So you look for a small parameter and then develop perturbative solutions. Right. But then I I ran into this book by Button. He's a resident. He was a resident famous applied mathematician, and Button had this paragraph at the end of his beautiful book, 500-page book, I think, the linear nonlinear waves. And then the last chapter in the book was had to do with the beautiful mathematical results developed for the theory of solid arms. So ingenious mathematical developments happened over there. And then after covering that, Peter makes this comment in concluding this chapter. One can only comment on the remarkable ingenuity of various investigators involved in these research developments. These results have given tremendous boost to nonlinear phenomena in general. Doubtless, much more of value will be discovered. Not the least is the lesson that exact solutions are still around, and one should not quickly turn to search for a small parameter. And I have in the bracket, allow me, or the computer. Exact solutions are still around, so we should not abandon such things. And I want to thank you all for your knowledge, patience, and stimulating questions. I'll be happy to any more queries you have.
We have a lot of questions in the talk. Are there any other questions?
Following up on the quote that you bring up, like, principle, people have simulated this in axis symmetry for like various types of systems. Bring up Ronnie Kaplan's did simulations in the 90s, and now people have done simulations for like winds from photomagnetizer. Something that you always, have you ever compared the solution directly? As in principle, you would be able to see this. Overplot this. I mean, people do this if you do the same type of analysis.
Yeah.
For like Lanford Payne type physics simulations. People have compared analytic solutions for these. So simplified this with actual simulations where you can do the entire analysis of that.
I have a lot of homework to do.
I'm just curious.
I will also check with you. Yeah, you too. Right? Yeah, this is the analyst first story. There are a lot of details to
Since you're keen about the Caltech connection, I can tell you Clauser. There's a prize at Caltech called the Clauser Prize. It's given for the best PhD.
Is that right?
And the two Clausers were brothers, twins actually.
Right, Frank
They're a
Clauser.
student of von Karman. Okay, the reason he got confused is one Clauser stayed around in aerospace, the other went to Johns Hopkins, but came back as a.
Oh yeah, there was a Clauser there too.
He's a division chair in engineering and applied physics here.
Yeah.
And yeah, so that's a Clauser. He's a very well-known person in Caltech.
Yeah.
And for many grad students, getting the Clauser Prize is like locally.
Oh, lovely. Lovely.
And the other one is after Parker's paper, the first verification came actually, I think, from Pioneer, and the scientists who discovered that I saw your references, Nogebore. She's the wife of, she's a well-known geophysicist, Marcia Nogebore. She's still around. I actually knew her when the husband was very well. And so that's sort of her main claim to fame, was the actual detection of solar wind in the early 60s.
I forgot to mention, when my article in American Scientist came, I got an email from Ted Gull.
Ted Gull, yeah.
Ted Gull, he was the original picture taker before Hubble. And then the picture qualities were really not good, so it didn't make too much dent. But he said at the time he came to Caltech and discussed.
Yeah. Again, they're also two brothers, it turns out. They're not identical twins, though. I actually know both of them.
Thank you for the history.
Okay.
Have another comment for a second? No? Okay, let's thank you. Thank you.